Okay, so picture this scenario for a second. You walk into this incredibly fancy
All
restaurant.
right.
You sit down and you order an absolute feast, like a massive multi-course meal. We are talking the premium steak, the lobster, the expensive wine, the works.
Sounds like a pretty good night out.
Oh, totally. But here's the catch. You finish eating, you wipe your mouth, stand up, and you just walk straight out the front door
Wait, without paying.
without paying.
Uh,
And nobody stops you. There's no check presented, no waiter chasing you down the street, no security. You just go home.
okay.
Then like 14 entire months later, the restaurant finally gets around to mailing you a bill for that dinner.
Mm-hmm.
And they just sort of cross their fingers and hope you're actually going to pay it.
I mean, a restaurant operating like that, they'd bankrupt themselves by the end of the month. It completely defies, like, basic business logic.
It sounds like a total joke, right?
Yeah.
But if you look at the multi-billion-dollar healthcare payment industry, that is literally their foundational business model.
Yeah, it's wild. So, welcome to the deep dive. Our mission for you today is exploring a really fascinating stack of sources we've got here. We're looking at technical documentation and architecture blueprints for a system called ClaimAuditAI.
It's a really interesting system.
It is, and we are going to unpack how this specific technology is fundamentally rewiring that archaic healthcare payment model using real-time AI, because, the financial numbers outlined in these sources are just absolutely staggering.
They really are.
And those numbers trickle down to affect every single person's premiums. So, where do we start with this?
Well, the documentation points out this frankly terrifying statistic right at the top. Somewhere between 3 to 10% of all national healthcare spending is just lost into the ether.
Wow, 3 to 10%.
Yeah. Entirely eaten up by fraud, waste, and abuse.
Yeah.
And the root cause of that massive systemic financial leak is exactly that restaurant scenario you just described.
Right.
The legacy healthcare system relies really heavily on what the industry calls a pay-and-chase model. Pay and chase. I mean, even the name makes it sound like you've already lost the battle before it starts.
Because you basically have. So the insurance payer disperses the funds to the hospital or the clinic first. The transaction clears.
The customer walked out the door.
Exactly. Then, typically, 14 to 16 months later, they deploy these massive teams of auditors to dig through the historical records.
Sounds exhausting.
It is. And if they find something that was fraudulent or, massively overbilled, they have to initiate this complex legal chase to try and claw that money back.
And I imagine the legacy software they use to flag these bad claims probably isn't exactly a sharpshooter.
No, not at all. The legacy rule-based engines have a devastating 30 to 50% false positive rate.
Wait, up to 50%?
Yep. They essentially just check, if a billing code is formatted correctly or if a required box is empty.
It's just a clerical check.
Pretty much. So human auditors end up just drowning in mountains of completely harmless, low-risk claims. While their really sophisticated million-dollar fraud slips right on by just because the paperwork happened to look tidy.
Right, the fraudsters know how to fill out the forms. So this is where the blueprints for ClaimAuditAI introduce a total paradigm shift.
Yeah, a complete 180.
Instead of that retrospective, backward-looking audit, the system uses real-time prepayment prevention. So it actively evaluates the medical claim before the transaction is even allowed to commit to the database.
And this is the crazy part. It completes that entire evaluation in just 150 to 400 milliseconds.
That's less than half a second.
Exactly. Before your metaphorical restaurant customer can even push their chair back from the table, the AI has audited every single ingredient of the meal. It verified the market price of the lobster, checked the history of the chef, and made a definitive decision on whether to hold the check or let it pass.
Okay, but I have to ask the obvious question here. If catching fraud before the money leaves the bank is so clearly the superior method, and it saves billions of dollars, why hasn't the industry been doing this the whole time? Like, it seems incredibly obvious.
Well, the barrier hasn't been a lack of desire, right? It's been the laws of physics and technical architecture. It's essentially a massive latency trap.
A latency trap.
Yeah. So in a traditional database environment, when a hospital submits a claim, the database has to take that payload, package it up, and send it out over a network connection to like an external API or a separate server that's running a machine learning script.
Which introduces travel time.
Significant travel time. That serialization, sending data over the wire, waiting for the external server to process it, and waiting for the answer to travel back, that takes seconds.
Right.
And if a massive healthcare network is processing, tens of thousands of claims a minute, you simply cannot pause a live database commit for 3 or 4 seconds.
You'd have a backup.
You would create a digital traffic jam that would bring the entire hospital's server architecture to a grinding, catastrophic halt.
Okay, so the engineers behind ClaimAuditAI, they had to figure out a way to completely bypass the travel time. So how do they actually do that without melting the servers?
They achieved it through a massive architectural breakthrough called embedded Python, and they run this inside their specialized InterSystems IRIS for health database.
Embedded Python, got it.
Yeah, so instead of reaching out across a network to external servers, the heavy machine learning packages like PyTorch, they run natively, directly inside the database kernel's own process memory space.
Oh, wow. So the brain is sitting right inside the living room with the data. There is no commute.
None at all. When a standardized FHIR healthcare claim, that's Fast Healthcare Interoperability Resources, when that claim is ingested into the system, a custom strategy intercepts the payload in the fraction of a millisecond before the database saves it.
Right.
The AI engines analyze the claim natively on the exact same server tier.
Hang on. I have to think about the mechanics of this for a second. Because if we are pausing a live high-speed database transaction to run a complex AI interception,
Yeah.
doesn't that risk creating a massive system failure if the AI tries to take an action? Like if the AI looks at a claim, decides it's fraudulent, and generates a hold notification, that notification is technically a new piece of data entering the system, right?
That's right.
So doesn't the database see that new notification and try to audit it, which would trigger another notification, and then just trap the whole system in an endless loop?
You've just identified one of the most dangerous engineering hurdles in real-time interception.
Oh, really?
Yeah. Without strict safeguards, intercepting a transaction to create a secondary resource, like a hold notification, it would trigger the exact same interceptor again.
Oh, man.
The system would spiral into an infinite recursive loop, exhaust the IRIS server's call stack, and just immediately crash the worker process.
A recursive death spiral is definitely not something you want in a system handling millions of dollars.
No, absolutely not. So the engineers built a brilliant safeguard. They strictly separated the execution memory into 2 distinct zones. They use a request context and an interactions context.
Okay, how does that work?
When the AI intercepts a primary claim and decides to flag it, it drops a highly specific thread-safe process private flag into a temporary memory vault.
The flag.
Right. The system reads that marker, executes the hold, and then immediately self-destructs the marker the exact moment the decision block ends.
It leaves no trace.
Exactly. It ensures the interception only ever fires on the initial organic claim coming from the outside world. It physically prevents the system from ever auditing its own internal epos.
Okay, that makes a lot of sense.
Yeah.
So it explains the how. That is how they intercept a massive financial transaction in under 400 milliseconds without triggering a server meltdown.
Right.
But we need to explore the what. Like, when this system actually pauses a claim, what is the AI looking for?
So the architecture uses a sequentially fired 3-tier AI engine. And Tier 1 is entirely focused on a massive blind spot. It tackles the unstructured data that legacy systems completely ignore. The actual conversational clinical progress notes typed out by the doctor.
Right. The blueprints call this the semantic clinical auditor. And it's designed to catch a very specific type of fraud called upcoding.
Yes. Upcoding is huge.
The sources provide a crystal clear example of how this works. Let's say a medical provider submits a bill for $2,500. And they use a highly specific billing code -CPT code 99291,
Okay.
which is for a complex critical care evaluation. That code explicitly implies the patient was in severe distress, requiring intensive life-saving analysis.
But if a human were to actually sit down and read the doctor's typed progress notes from that exact visit, the text might simply say, patient arrived for routine yearly physical checkup. All vitals normal.
Right. And in a legacy system, that claim gets paid automatically.
Yeah.
The billing codes are formatted correctly, the required boxes are checked so the computer just rubber stamps it.
Because the old system doesn't understand the nuances of human language, it just sees a valid code.
Exactly. But Tier 1 of ClaimAuditAI changes that.
It does. It uses a local sentence transformer model. It takes both the official description of that billed CPT code and the doctor's messy, unstructured clinical notes, and it translates both of them into mathematical vectors.
This concept is wild to me. It takes paragraphs of English and turns them into a massive multi-dimensional mathematical map.
Specifically 384 dimensions.
384 dimensions.
Yeah. And once those words are turned into points on a mathematical map, the system can measure the physical distance between them. If the concepts are similar in meaning, the points will be clustered close together.
Okay.
The system uses a native SQL function called a vector cosine and an HNSW vector index to calculate the exact distance between the doctor's story and the doctor's bill.
And it does this essentially instantly, right? Because it
Yep.
doesn't have to read the words anymore. It just calculates the geometry.
Exactly. And the documentation notes a very specific threshold for this. If the semantic similarity score between the build procedure and the actual clinical notes falls below 0.38,
0.38, got it.
the system instantly knows the narrative doesn't match the money. It immediately flags the claim for a clinical procedural mismatch.
Okay, but, and hear me out here, if I'm a really sophisticated fraudster and I know the system is reading my notes, I'm just going to make sure my notes are perfect.
Right.
Like, I will write a beautifully detailed, complex surgical note that perfectly matches my complex surgical billing code. But then I'll charge $50,000 for, like, a standard surgical tray.
Ah,
The words match. The meaning matches. But the math is entirely fictional. Semantic analysis can't read meaning into a purely inflated price tag, can it?
no, it can't. Which means semantic analysis just hit a wall in your scenario. You cannot use a dictionary to catch a math problem. You have to measure the numbers, which brings us to Tier 2, the statistical outlier profiler.
So we're moving from words to numbers.
Yes. This tier abandons language entirely and uses an unsupervised PyTorch autoencoder to profile extreme financial anomalies.
Wait, unsupervised, meaning the engineers aren't giving it a list of bad behaviors, right?
Right.
Like it has to figure out the patterns of normal human behavior completely on its own.
Exactly. The autoencoder takes 5 specific dimensions of a claim. It takes the total billed amount, the number of individual items on the bill, the patient's age, the duration of the visit, and the specific specialty of the doctor.
Okay, 5 dimensions.
It takes those 5 dimensions and mathematically compresses them through a tiny bottleneck. Then it attempts to reconstruct the original data on the other side of that bottleneck.
It kind of reminds me of forcing a highly detailed clay sculpture through a tiny square mold, and then you try to rebuild the exact sculpture on the other side using only the squashed clay.
That's a great analogy.
Because if you are used to making simple cubes every day, reconstructing a cube is easy. But if you suddenly try to shove a wildly complex, spiky statue through that same square mold, what comes out the other side is going to look completely deformed.
That perfectly describes the mechanism. The model trains its mold on thousands of normal, everyday historical billing claims.
Right.
When it suddenly encounters an extreme financial outlier, a bizarre statue it has never seen before, it lacks the learned patterns to reconstruct it accurately.
I see.
So the mathematical difference between the input and the garbled output is what they call the reconstruction loss. It uses mean squared error. A high reconstruction loss definitively equals a massive anomaly.
Okay, but wait, I see a massive logical hole here.
Okay, what is it?
If I go to a general practitioner for a standard flu shot, a $2,500 bill is a massive glaring anomaly.
Right, definitely.
The autoencoder would freak out.
Yeah.
But if I am the critical care unit, a $2,500 bill is perfectly normal. It might even be suspiciously cheap. So if the AI is just hunting for large numbers and high reconstruction loss, isn't it going to accidentally flag every single specialized brain surgeon and trauma center in the entire hospital network?
In a rigid rules-based system, that is exactly what happens, which is why human auditors get so overwhelmed with false positives.
Right.
But the engineers solved this by implementing dynamic threshold logic. The anomaly threshold isn't a static number. It adapts on the fly.
Oh, really?
Yeah. The engine isolates the provider's specific specialty code and calculates a unique threshold based on the 95th percentile of the historical mean loss for that specific medical field.
So it basically forces an apples-to-apples comparison. It only compares a general practitioner's bill to other general practitioners and a neurosurgeon to other neurosurgeons.
Exactly. Completely eliminates that cross-specialty noise. But they had to add one really vital mathematical safeguard to this tier. They gave the dynamic threshold a hard minimum floor of 0.02.
0.02. Why does the floor matter?
Because if you have a highly homogeneous clinic, say like a pop-up vaccination site that charges the exact same $40 fee for every single patient thousands of times a day, the variance is incredibly low.
So the AI would get used to exact perfection.
Exactly. The AI's calculated threshold might drop all the way to 0. It would become hypersensitive. The 0.02 floor ensures that even in those really rigid environments, the model doesn't start flagging perfectly normal claims just because the data was slightly too predictable.
Okay, so we are catching the individual liars with Tier 1, and we're catching the individual price gougers with Tier 2.
Right.
But that still leaves the biggest financial drain on the system. Like, what happens when multiple doctors, clinics, and pharmacies are all in on the scam together?
Yeah, relational multi-party fraud, basically organized crime syndicates operating within the healthcare system.
Exactly. And to catch that, you have to stop looking at individual claims in a vacuum
Yeah.
and start looking at the entire ecosystem. Which brings us to Tier 3, the collusion network mapper.
This is where the architecture utilizes a Python library called NetworkX to build directed multigraphs.
Multigraphs.
Yeah. The system steps back and maps out the hidden relationships between referring doctors, providing clinics, patient addresses, and the actual flow of financial claims connecting all of them.
It's like a digital version of a detective's corkboard,
Yeah.
of the one covered in red string connecting all the suspects.
Exactly like that.
But it's not just a static picture. It's a living, breathing map that actually measures the gravitational pull between these bad actors. And instead of taking a human investigator 6 months to pin up the photos and trace the string, the database generates and analyzes the entire web in milliseconds.
It's incredible.
So what kind of invisible behaviors does this network graph actually illuminate?
Well, it reveals anomalies that are physically impossible but financially devastating. First, it catches what they call geotemporal leaps.
Which are...
The graph will instantly highlight if a single patient is billed for complex, in-person services at 2 different clinics located, say, 150 miles apart on the exact same afternoon.
Right. Unless the patient owns a private jet or a teleporter,
Yeah.
that is physical fraud. You simply cannot be in 2 places at once.
Exactly. The graph also flags address sharing. It'll light up if it detects multiple supposedly disconnected medical providers all registering their operations out of a single residential home address or a random P.O. box.
Oh, that's a huge red flag.
And it's incredibly effective at spotting referral cycles.
Referral cycles.
Yeah. This is a predatory pattern where a closed loop of providers endlessly refer the same cohort of patients to each other, round and round, just to maximize diagnostic billing without ever actually providing any real therapeutic care.
Wow. Okay, so we have semantic analysis, statistical autoencoders, and network mapping, all firing sequentially in under 400 milliseconds.
Yeah.
But how does the system actually synthesize all of these different red flags to make a final unified decision on whether to freeze the money? Like, who makes a final call?
The AI orchestrator uses a really elegant scoring synthesis. It assigns specific weights to each tier's findings.
Okay.
So if Tier 1 finds a semantic mismatch, it adds 0.35 to the threat score. If the autoencoder in Tier 2 finds an anomaly, it adds another 0.35. And Tier 3's network graph can add 0.30.
Okay, so it adds them all up.
Right. If that combined weighted score hits or exceeds a threshold of 0.35, the claim is instantly held. The system physically intercepts the outgoing communication and mutates the HTTP response to a 202 accepted hold status.
202 accepted.
Yeah. It ensures the payout is entirely bypassed.
It accepts the paperwork, but it puts a hard lock on the vault.
Exactly.
But here is the next massive hurdle. If the system holds a $100,000 claim, it has to explain why to a human auditor. And the blueprints mentioned it uses a large language model to generate a detailed human-readable report explaining the exact nature of the fraud.
Right, it creates a markdown report.
But wait, if we're talking about an LLM writing a comprehensive report, that takes massive compute time. Like, it takes me 10 or 15 seconds just to get a simple email drafted by a chatbot.
Oh, for sure.
So if a hospital uploads 10,000 claims in a bulk batch at midnight, and the system pauses for 15 seconds on every single flagged claim to write a customized essay, the API gateway is going to time out. The whole pipeline would shatter before it finished the first 100.
The server would absolutely crash under the weight of generating those text explanations. It was a critical bottleneck.
So how do they fix it?
They implemented what they call just-in-time, or JIT generation.
They delay the essay writing.
Exactly. During that initial 400 millisecond transaction, the system flags the claim and saves the raw mathematical threat scores. But it completely skips the slow LLM text generation.
Smart.
It only invokes the LLM to write the long-form explanation just in time. Literally the exact moment a human auditor actually logs into the dashboard and clicks into that specific claim to review it.
Wow. So the system does the math instantly to stop the theft. But it only writes the essay when the teacher actually asks to read it. That saves massive amounts of compute power.
It's incredibly efficient.
But what about the security of the patient data? Because sending highly sensitive medical histories out to an external cloud AI to write that essay seems like a catastrophic IPA privacy violation just waiting to happen.
Well, the security boundaries are actually ironclad. Absolutely no identifiable protected health information, no PHI ever leaves the secure hospital environment.
Not at all.
None. The vector matching for the clinical notes we talked about in Tier 1 happens entirely locally. And when the system finally does ping the external LLM for that just-in-time summary, it violently scrubs the payload.
Okay, so what does it actually send?
It only sends non-identifiable abstract metadata, like the raw billing codes, the financial amounts, the specialty category, and the anomaly metrics.
Okay, that makes sense. But when it
Right.
comes to the human element, who actually has the power to look at this dashboard and override the AI?
That's a great question.
Because if an AI freezes a massive payout to a really powerful hospital, you can't just let an intern click an approve button to make the alert go away.
Definitely not. The system utilizes SMART on FHIR cryptographic access tokens to enforce a really strict 5-level numeric role hierarchy.
So levels.
Yeah. So a level 1 viewer, they can only see basic generalized statistics on a dashboard. A level 2 auditor can look at the held claims and write notes, but they are physically locked out of the approval mechanism.
So who can approve it?
You have to be an authorized director, so that's level 4 or higher, to actually approve an override and force a payment through. And doing so leaves a permanent, tamper-proof fingerprint on the ledger.
Okay, wow. To sort of summarize the journey we have been on today for you, we started by looking at a multi-billion-dollar problem. An archaic, leaky pay-and-chase system that hemorrhages money simply because it waits a year to ask questions.
Right.
And the solution outlined in these technical blueprints is a millisecond-fast embedded AI interceptor. It stops the massive financial leak right at the source.
Before a single dollar is transferred.
Exactly. Before the money leaves the bank, it reads the semantic meaning of the doctor's notes, it tests the statistical reality of the math, and it maps the relational network of all the bad actors involved.
It represents a fundamental shift from a reactive posture to a proactive defense.
It really does.
And, it leaves us with a really provocative final thought to consider.
Oh, what's that?
Well, this deep dive showed how embedding real-time AI directly into a transactional database can fix the broken integrity of healthcare payments, right?
Yeah.
But if AI can accurately adjudicate wildly complex, multi-tiered medical claims in under 400 milliseconds, what other massive foundational systems in our society are currently limping along on outdated pay-and-chase models?
Oh, that's a really good point.
Think about government tax refunds or massive insurance payouts or bureaucratic grant distributions. How many of those bloated systems are just completely ripe for a real-time AI overhaul?
That is a fascinating thing to think about. Because right now, in so many of those massive industries, we are still just sitting back, letting the customer eat the steak, walk out the door, and just blindly hoping they decide to pay the bill a year later.
And it is definitely time to close the tab.